let this start. It always takes about 10 seconds or 15 seconds to start the recording. I don't know why. Today it's not even started. Do you think it's give me 1 second. Sorry about this. Okay, what I wanted to say is that try, now we're at the 5th or 6th or whatever it is lesson, try to bring all of the concepts together. So when I introduced the idea of fundamental equation, okay, of a thermochemical system, okay, of some kind, of a chemical system. There was a very specific reason, okay? And the reason is this. Well, you've seen that we have, depending on what case we're interested in, constant temperature and pressure, and so on, or isolated system, we have a very specific condition of equilibrium, okay, using either entropy or internal energy. And for all of those, you can come up, you can construct, okay, fundamental equation. The fundamental equation is the expression, essentially, through the use of equations of state, okay, of a function, okay, a function which is usually expressed in a phase space, for example, comprised of internal energy, number of moles, okay, and other, and volume, for example, which are the three main sort of extensive quantities. But it could also be expressed, as we've seen for constant temperature and pressure systems, in terms of the Gibbs energy, the minimum of Gibbs energy. So if you have the fundamental equation, you can actually represent it in this space and find the minimum point, okay? That is why we're doing this, okay? So very slowly, okay, we're moving towards a point where we will be able to actually write down, okay, explicitly for a particular system, the fundamental equation in terms of the Gibbs energy. In fact, let me share my blackboard. Wait a minute. Sharing is not the easiest of things. Okay, can you see it?
Yes.
Tell me yes, yes or no? Yes. In particular, we've seen that given a system, okay, you can actually perturb its composition, okay, through the concept of chemical reactions, okay? So think of chemical reactions as something similar to what we've called walls, okay? The walls can sort of perturb a system, drive it off equilibrium somehow. And then remember that we release the internal constraint. It's obviously visually easy to picture this internal constraint as a piston, but you can also consider it as keeping the composition constant, okay? The only way you can perturb the composition is clearly not through a wall, okay, like a rigid wall, but it's through a chemical reaction. So that's why we're using the concept of chemical reaction, okay? And essentially, we've introduced those as not collisions between molecules, as we said, but as really statements of conservation of atoms. That's what we did. So these are just particular ways in which you can actually have those molecules interact with one another and react, okay, as long as the total number of atoms is conserved, okay? So why did we introduce this particular concept? Well, not only the concept of reaction, but remember, we also introduced the concept of progress variable. Now, this is an independent variable that actually it's very useful, very handy, because it can actually represent an independent variable which when it changes between its lower bound and its upper bound, okay, really spans all of the possible compositions that can arise, okay, through the action of this particular reaction. So in very lame terms, if psi, if you remember, is all the way shifted to the left, you remember the concept of slider, okay? In some sense, it's like shifting left to right, shifting the piston, only that we're not shifting any piston, we're shifting the composition, keeping the number of atoms constant. Maybe that's clearer. So if you're all shifted to the left, what happens is that now you run out of products. So this guy is 0, okay? And you have basically just hydrogen and oxygen. If you shift the slider all the way to the right and the chemical reaction is all shifted to the right, then one or the other of the reactants, maybe oxygen or maybe hydrogen, runs out. And so you just have water, possibly, and some left over of the other reactant. Okay? So clearly now, in theory, okay, or ideally, I can set this value to whatever I want. But the system, if I let it evolve naturally, if I release the constraint, will find its own point of equilibrium at the minimum Gibbs energy, okay? So if we can write, for example, the Gibbs energy as a function of the progress variable, then it's really done, okay? All you have to do is find the minimum. When you find the minimum, you will find the value of the progress variable that corresponds to the equilibrium, okay? Again, don't worry if you don't catch all of this, because we're going to actually be doing it. So we introduced the concept of progress variable. So now we can actually write the composition N1, N2, and 3, so the number of moles of species 1, 2, and 3, hydrogen, oxygen, and water, as a unique function of this squiggle, which is supposed to be psi, okay? In fact, you can actually rewrite this in a vector kind of form, and we'll see why this is handy. Okay, for this particular case, we did a particular, someone is trying to get in. Please be on time again. We chose the initial composition, okay, exactly equal to the stoichiometric coefficients. Now, what that means essentially is that we chose N1, 0, the initial number of moles of hydrogen, as being 1, okay? Exactly like this coefficient. This is a particular case. You can choose any other, and I'll show you how in a second. So initial number of moles of oxygen, 1/2, and initial number of moles of water. In this case, we can choose it to be 0. So you just have reactants initially, okay? So you can write down the number of moles as a function of psi, and you see now that psi essentially varies from 0 to 1. Now, the fact that it varies from 0 to 1, it's not always the case, okay? It's a particular case of this choice here that we've made, okay? The choice of initial composition equal to the stoichiometry. In fact, we can come up with a general case, any case, but let me just point out here the fact that if you can see the slope, let me see if I can write here, dn2 by dxi is equal to minus a half, if you see, and on the other hand, dn1 by dxi is minus 1. So you see that essentially this slope here, okay, is minus 1, and this slope is minus a half. Essentially meaning that because of the stoichiometry, okay, because of the fact that you have a half here, so for every molecule of hydrogen, you only have a half of molecule of hydrogen, it means essentially that the variation of hydrogen moles is always twice, okay? And this is reflected by the slope of this curve. Now, this clearly is number of moles, okay? Now, what happens, for example, if we have a generic initial condition, not just 1, a half, and 0. So let me rewrite N1 is essentially, which is NH2, okay, is equal to NH2 initial, so the initial number of moles of H2 minus psi, okay? N2, which is the moles of oxygen, will be the initial number of moles of oxygen minus 1/2 of psi, okay? And then water, H2O, is equal to the initial number of moles of water plus psi, okay? Clearly, the slope here is inverted, okay? Because we have a plus sign, simply because this is whatever is in front of here is the difference between nu double prime minus nu prime. So it's the stoichiometric coefficient on the product side minus the stoichiometric coefficient on the reactant side. Of course, being this a product, as psi increases, you have that the reactants decrease, okay? And obviously the product increase. We're going from left to right. Okay. Now, these are generic. So, for example, well, let me do it. Let me draw. Now, obviously, you have to bear with me. I can't draw straight lines. So I'll just try and. There must be something wrong with this thing anyway, but okay. So this is psi, okay, and somewhere we have the y-axis here, which is over here. So this is the number of moles, okay, and this is psi equals 0. So as you know, psi equals 0 corresponds to the initial number of moles. Okay, so really now there is absolutely no constraint on whatever number of moles you want to choose. Okay, I mean, it's your choice, right? So you're just introducing a certain number of hydrogen and oxygen atoms distributed in molecules. So you can even add, for example, some water at the beginning. Okay, so suppose I'm just doing this randomly. Suppose this is, for example, the initial number of moles of water, H2O, okay? This is the initial number of moles of O2, okay? And over here, for example, we have the initial number of moles of hydrogen, okay? Well, we know that N1, N2, and 3 have their own particular slopes. Okay, this is minus a half. This is -1 for hydrogen. Okay, and so essentially, we can redraw these lines. Okay, so as long as you draw, for example, a line which has slope. Knows if I can. There's probably a ruler here somewhere. Let me just. Whoa. What am I supposed to do here? Do you have any idea how to use this? Okay. Very good. I mean, for me, if it's not immediate, I think it's just stupid. Anyway, so I'm just drawing now a. I'm so sorry. I just. I'm trying to draw a line here which has slope equal to +1. Okay? So that's essentially your number of moles of water as psi increases. Okay? Then you have the same kind of slope. God knows how I'm going to be doing this. Like this. God. Maybe I'm going to ask you for a pause, maybe at 11, so that I can try and figure out how to set up this thing, because there must be, you guys, I mean, you're younger than me, far younger than me. Don't you have advices on how to use this better? Hello?
Yes, yes, Professor. For scaling, we can just select the scale.
You mean the ruler?
Yes, ruler.
Yeah. And then what?
Just make it straight, because it can give angle also.
Yeah, but how? What do I do?
Just you need to clockwise or anti-clockwise rotate it.
But
it is not a screen touch. It moves with rotation.
Yeah, okay. I can sort of see it. Okay. So now, if I want to rotate this.
Yes, you can rotate it at what angle you need.
Yeah, but I rotated pressing what what button?
No, actually, it just rotates with a finger touch.
Finger touch?
Yes.
Finger touch stylus.
I'm sorry, but I don't have a touch or sensitive tablet.
Oh, you can rotate. Try to rotate with the pen if it works. Because what I remember in my pad, it just rotates with the.
I can only move it, but it stays at 45.
Oh.
Double click the stylus and then try to rotate it.
Okay. Stylus pen, right click is there.
Right click.
And try to.
Left click. No click.
Yeah.
Maybe I have to kind of touch some stuff that I don't know.
Just a minute. I also have same function, but it.
Professor, can you try clicking on the angle that is showing on the scale, 45?
Well, yeah, but you see,
Yeah,
it's
on
not.
the angle that is written 45 on the scale. Just try to click it on that.
I'm clicking everything. Does nothing happens.
Oh, sorry.
Okay, forget it. Anyway, um, this is clearly half. Okay, the slope. Okay, so you'll do it better than I do. Okay, than I will do because clearly I can't draw straight lines. But anyway, now look at what's happening here. Okay, suppose I'm driving now the reaction completely to the left. Okay, so I take psi and I decrease it, decrease it, decrease it, decrease it, decrease it like this. Okay, at some point, you see what's happening with the water. At some point, the product, which is water, will be zero. Okay, it will be completely exhausted, or there will be any of those left. And clearly, you cannot go into negative concentration. So clearly, this is my lower bound. Okay, and this is clearly psi left. Okay. On the other hand, now if I move to the right, and you see that for every psi, I have, a composition, okay, that I can read off this chart. At some point, however, look, I'm going to run out. In this particular case, owing to the choice of the initial number of moles of oxygen, okay, I'm running out of oxygen. So now clearly the reaction cannot go any further because no oxygen can react with hydrogen. So we have to stop here. Okay? So essentially, you cannot consider any composition on the left of this and on the right of this. Okay? And this is psi right. Okay? So on this particular case, okay, we were moving between psi equals 0, psi at left was equal to 0, and psi right was equal to 1. In this particular case, if you think about it, I don't know what these numbers are, but psi left is even less than 0, okay? Because this is psi equals 0, so it's a negative number, okay? And I'll show you later on how to actually determine numerically psi left and psi right. It's nothing really too strange about this. Let me add another few, and you can play around. You can play around with different compositions. Okay. Initial composition. You can, for example, increase the number of moles of N0, and then you'll see that now the so-called limiting reactant will not be oxygen anymore, but it will be hydrogen. Okay, so psi R will move, for example, to here. Okay. Okay. So in fact, let me just write this as a definition. So when we have to stop in the left or lower bound here, it's because we have H2O acting as the so-called limiting product. Okay, H2O is a product. It's on the right side of the equation, and clearly, if you go all the way to the left, at some point you will run out of this product. Okay, you can go any further. So the product is limiting the reaction to stop. Okay. On the other hand, by construction, this point here will be due to the fact that O2 is the limiting reactant. Okay, O2 is on the left side of the reaction. We all move the reaction towards the right, and at some point, one of the two, either O2 in this particular case, but also it could also be H2, can run out. We cannot, therefore, proceed any further with the reaction. Okay, we have to stop. One other thing that you obviously should notice is, well, go back to the definition of progress variable. Okay, now, if you consider the differential of psi, this is simply dni, right? Divided by these stoichiometric coefficients, right? Now, it's obvious that if the species I, okay, is a reactant, okay, the definition of reactant is something that sits on the left side of your reaction, okay? If you remember the notation, this is the stoichiometric coefficient of products of species that are on the right. So in this case, dxi will be equal to dni divided by 0 minus, okay, nu prime. So you see essentially that dni, therefore, and dxi have different signs because there is a minus sign here. This simply means that all reactants decrease, okay, as psi increases. So as psi increases in this direction, they have a negative slope. These are the reactants on the left side, exactly like oxygen and hydrogen. If it's a product, it's clearly the opposite, okay? If it's a product, dxi is equal to dni divided by nu double prime minus 0, okay? So clearly in this case, if dxi is bigger than 0, then dni is less than 0, and in this case, if dxi is positive, so moving again from left to right, dni is bigger than 0, so it increases, okay? Now, let's go back to this problem here, okay? Because we had said that actually we can take advantage of a three-dimensional representation of this, okay? How do we do this? Well, let's construct our phase space, our composition space, okay, like this, where essentially we have, well, it's an arbitrary choice, but we can have, for example, N1, N2, N3 in this way. This is clearly three-dimensional space, okay? So now I hope you agree that we can actually represent this function here in 3 dimensions. How do we do this? Well, we start from the initial composition, okay? Remember, the initial composition was 1 mole of N1, which is hydrogen. So we go all the way here, for example. This is 1. And half a mole of oxygen, right? So, and no moles of water. So we are in this point here, okay? At the end, okay, we have 0 moles of both. So the oxygen and hydrogen get depleted at the same time, you see, okay? And so we have 0 moles of hydrogen and oxygen, and 1 mole of water. So we are here essentially on this axis. Okay, so now of course I will have huge trouble. Oh God, nothing. I will definitely try and, well, imagine that this is a straight line, okay?
Professore, forse può ruotare il righello con la rondella del mouse.
E chi ce l'ha il mouse?
Ah, bene.
Io ce li
Magari
provo.
là col doppio dito, forse scorrendo sul doppio dito col pad, forse, non lo so.
Proprio no.
No,
Ma
niente, però
le ho
col
provate
mouse.
tutte. Non lo so, che per esempio qua mo c'è un... No, ma probabilmente è nei setting, capito? Adesso devo trovare un
Probabile, sì.
modo. Allora, comunque, I hope you... So this is our initial point, 1/2, 0. This is our final point, okay, which is 0, 0, 1. And, well, we can even start from the origin and point to the initial point. So this would be my vector n, 0, clearly. And any point on this line is what? Is n. Okay, so if I go back to my attempt to, do you remember this? To represent this vectorially, we have that vector n is equal to what? Is equal to the initial vector, n0, plus, now look at this, we have a stoichiometric vector, okay? And then, essentially, a scalar, which tells me how far into the stoichiometric vector we are. So you see that essentially this vector here is nothing else but the stoichiometric vector times psi. So suppose we stop here, okay? Here psi, we said it was 0. Here psi is 1 because we are at the initial point, okay? All the reactions all shifted to the left. And then we move along this stoichiometric vector all the way down to 1, okay? And we get to this point here. So it turns out that my stoichiometric vector uniquely represents a reaction, which is nice, I think, because now I know that essentially vectors in R3, okay, special vectors in R3, are like a rail you have to follow, and each of those represents a different reaction. And really, you're guaranteed that by staying on this vector, okay, the conservation of atoms is always guaranteed, okay? And again, if you don't understand fully, you will in about 10-15 minutes when I will make more examples. Now, this is a particular case where essentially we were starting from this particular initial condition, but really there is no reason why this should not be completely general, okay? So again, you can draw, it's not a pleasure for me to draw this stuff, but still, okay? You will try and interpret. it's a shame that we cannot be in the classroom for this reason. Okay, I mean, to be honest with you, I spent a lot of time past semester trying to figure out how this thing works, but I'm not just good. I'm not good with this thing. So there's nothing I can do. I could learn, but still, I think I have learned, and I'm just not good at it. Sometimes you have to face reality. Okay, so this was, I'm just redrawing this this situation here, and again, this is the starting point, but we could have started anywhere. For example, we could have started up here, right? We could have started at, oh God, at 1, okay? And what happens? Well, look at this. All we changed now between the previous situation and now is that we switched from this particular initial condition and 0 to this one. But other than that, okay, now let me erase that a second. We will be following the exact same direction, exact same reaction, okay, over here, and we'll end up somewhere here, okay? So this is still my vector ni, okay, my direction ni, okay? And you can do whatever you want. You can start from, say, somewhere here, okay? And now it's not very easy to see, but as you've noticed, in this previous case, I had to stop when I meet one of the planes. Now, clearly, hitting a plane means that you have to stop because one of the species is totally depleted and you can't go any further. In this particular case, okay, we're still going in the direction of nu, but then we have to stop at this lower point here, okay? In this particular case, the limiting reactant, let's see if you've paid attention. This is N1, this is hydrogen, okay? This is N2, which is oxygen. So now the fact that we have to stop is because the limiting reactant is oxygen, because you see, we've hit the rock bottom, okay, where O2 is 0, okay? So you can have fun in doing all sorts of things, okay? So it turns out that in multi-dimensional space, okay, where each axis represents the species, a particular direction will represent a reaction. Now, clearly, not any direction, okay, will represent a reaction, okay? And I'll show you in a second. Each direction represents essentially the conservation of atoms, okay? It's not the only way in which you can represent the conservation of hydrogen and oxygen atoms, but it's one way, okay? So I cannot pick, you know, the composition in R3 at random, okay? I cannot move around freely, okay, in R3 at all, okay? If I have a certain initial composition, I must follow this direction. Otherwise, I'm creating or destroying atoms, and I cannot do that, okay? Now, as I move the initial composition around, I hope you can see that corresponds to the scalar, to the progress variable psi left, and this is psi right. So essentially, I can move along this direction, exactly like this guy tells me. Okay, this, we'll just put it in a box because it's the most important relationship. So if I substitute psi left, I will be essentially here, okay? And if I substitute psi right, I will be over here, okay? And we don't know what these are. We'll have to find them, but they vary. They vary as you vary n0, exactly like we saw here. Okay, so the values of psi left and psi right depend on the particular choice of initial condition for a given reaction. Okay, let's see now. Well, I'll tell you what. I'll give it a break here, because I really want to figure out. I should have done it alone before, but give me 5 minutes of break. I just want to figure out how this thing works. Okay, should I maybe stop the recording? And then I'll, in the end. Okay, so let me now try and explain why we're actually moving on a straight line. Why is it that essentially a reaction that conserves, or a stoichiometric relation, which we call reaction, okay, that conserves atoms, okay, atomic species, why is it that it essentially corresponds to a line, okay, in the composition space? So maybe we can write it here. Why a line? Okay. So this is what we have to conserve, okay? Hydrogen atoms and oxygen atoms. Okay? Must be conserved, okay? So let's see how we can express some vague or naive concept of conservation of atoms. So take, for example, an initial composition N0, okay? It could be anything, but for the time being, for simplicity, let's stick to my 1/1/2, okay, and 0, okay? So this is the number of moles of H2, this is the number of moles of O2, and this is the number of moles of H2O that we have to start with, okay? So in order to understand how we can conserve the atoms, we first have to calculate how many moles of hydrogen atoms and oxygen atoms I have. Not of molecules, this we know, but of atoms. So the way to do that, and this I will call initial elemental composition. Okay? So the initial number of moles of hydrogen atoms, okay, will be the following, okay? Well, we take the number of moles of hydrogen, okay, and we multiply by what? By the number of hydrogen atoms that we have in the hydrogen molecule. So I have to multiply by a special number here. In this case, clearly it's 2, because we have 2 hydrogen atoms in each molecule, okay? Now, let's go to the oxygen atoms. Now, remember, we're looking for the total number of hydrogen atoms, okay? So let's see. we have 1/2 mole of oxygen, but how many hydrogen atoms do we have in the molecule of oxygen? We don't have any. So the special number now here is 0, clearly. Now, on the other hand, here, we have, let me, sorry, I have to stop a second because there's someone knocking at the door. Can you stop? Can you give me a second? Sorry. So let's go back to water. Can you hear me?
Yes.
Okay. So we have 0 moles, okay, initial moles of water, okay? And how many hydrogen atoms in this molecule of water? 2. Okay. So again, this amounts to essentially 2 moles of hydrogen atoms, okay? Now, we can do exactly the same with oxygen atoms, the initial number of moles of oxygen atoms. We have essentially, again, I'm just writing everything in full because later on you'll realize this can be written in matrix form, okay? So we have 1 initial mole of hydrogen, but 0 clearly is the number of oxygen atoms in the hydrogen atom, okay? Then I have 1/2 initial mole of oxygen molecule. How many oxygen atoms in the molecule? 2, okay? And so on, okay? 0 times 1, okay? So initially I only have 1 mole of oxygen atom, okay? So now we know that 2 moles of hydrogen atoms and 1 mole of oxygen atoms are being introduced in my system, okay? Now, I always now need to conserve these quantities of atoms, okay? Obviously. How do I express this? Well, there are really 2 constraints. Think about it. Now, whatever the composition is, I still have to conserve these quantities of atoms. So I have a constraint number 1, which is that the number of hydrogen atoms, okay, for a given composition will always need to be equal to the initial number of hydrogen atoms. Now, how do we, this is my constraint. How do I express the generic number of hydrogen atoms? Very similar to this. Now, I will have, generally speaking, for a generic, by generic I mean for any value of the progress variable psi, okay? I will have NH2 moles of hydrogen, which I have to multiply by by 2, which is the number of hydrogen atoms in the hydrogen molecule, right? So I'm doing exactly the same here, okay? As I'm doing before, but with a generic number of moles. So I have now number of moles of oxygen. How many hydrogen atoms do I have in oxygen? 0, okay? And then I have moles of H2O, okay? And in this case, how many hydrogen atoms do I have in H2O? Well, 2, okay? And this will be, well, will be equal to N0H, which is clearly 2, okay? Now I can do exactly the same with the oxygen atom, okay? Will have to be equal to the initial number of oxygen atom. So I just now write down the number of H2 moles. Now, how many oxygen atom in H2? 0. Okay, so on and so forth. Okay, and O2, how many oxygen atoms in O2 is 2. Okay, H2O, how many oxygen atoms in H2O? 1. And this will be equal to the number of moles of oxygen atoms that we've introduced, which is 1. Okay? So, in fact, I can anticipate that this can be written as a matrix, okay? I don't know if you've noticed, but it's a 2x3 matrix which multiplies essentially my composition vector, okay? Okay, but we'll see the matrix form later on, okay? So for the time being, let's look at my 2 constraints, okay? We have to follow whatever the composition is, these 2 constraints, okay? Let's write them a little bit better. So this would be, for example, the first one is 2 NH2. This is 0, okay, plus 2 NH2O, okay? This will be equal to 2. And this would be 2 NO2, sorry, that's not a 2. Plus 1 times NH2O, and this will be equal to 1. Now, what do these represent in 3D space? Okay, so this is the conservation of H atoms, and this is the conservation of O atoms. Now, any constraint, okay, between 2 variables in a 3D space is a plane, and I'll show you now in a second, right? So we have plane 1 and a plane 2, okay? So it's no wonder that my reaction is really the intersection, a line, which is the intersection of 2 planes, okay? Let's see if I can draw this. Now, let's see if we succeed. Well, it's going to take, I mean, it's going to be straight, but it's going to take an hour. Oh my God. Okay. So let me just write down, okay, this is the axis. Forget it. Okay. It's very depressing, I tell you, because it's going to turn, it takes me about 1 minute to turn this thing over. So it's really pointless. Okay, let's see if I can do something, okay? This is my axis, okay? Again, this was N1, which was representing hydrogen. This was representing oxygen, and this was representing H2O, okay? Now, let's look at the conservation of hydrogen atoms, okay? let's look at this equation here. What does this represent in this space here? Well, suppose that NH2O is 0, okay? You see that NH2 must pass through this point here, okay, which is 1, okay? On the other hand, suppose NH2 is 0, okay, H2O must pass towards this point here, which is 1. So really what this equation is this plane here. I hope you can see it. Okay, this plane here, okay, I'm extending it, but this plane here, what it really represents is the conservation of H atoms. So for clearly, this only holds for the particular initial condition that I chose, clearly, which is, remember, this one, okay? Now, as long as I move on this plane, I'm conserving H atoms, but I'm not necessarily conserving O atoms, okay? So let's look at the second plane, okay? So for example, suppose that H2O is 0, okay? So clearly the intersection now is of N on the NO2 axis is 1/2, so we're here somewhere, okay? And suppose that NO2 is 0, clearly the intersection is still this point here. So again, it's a little difficult, but I'll try. Maybe I'll get better, I don't know. So you see now that we have this particular plane, okay, which represents the conservation of oxygen atoms. Okay, so if I move around on this plane, I'm conserving O atoms. So now, if I want to conserve both, there you go. I have to join these 2 points. I hope I'm not doing anything. Okay, I sort of. Okay, so this is the intersection. So you see now that the intersection that conserves both, okay, is a line, okay, is a line. Now, this was my initial condition, of course, well, more or less, this is my initial condition, okay, so this was the line that we drew before, okay, this is my reaction. So I'm starting from here, okay, I'm ending up here, okay? So here we conserve both atoms, okay? Very good. So I hope that the geometric at least intuitively, the geometric approach is clear in spite of my absolutely horrendous diagrams, okay? So if I go all the way up here, you'll recognize exactly the same kind of direction, okay? Now, they're horrendous diagrams. I will generalize now this. I won't obviously proceed with this elementary kind of approach, point-by-point approach. I will obviously generalize this to a sort of a linear algebra kind of approach, which will involve that matrix that we saw, okay? I'll do that later. For the time being, I'd just like to essentially go back to, let me just, yes, right, to the concept of equilibrium, because it's always very important not to lose sight, okay, of what we're doing here, okay? Remember, okay, for a constant PT system, okay, that we have figured out that when we let the composition evolve spontaneously, the system will evolve so that dG, okay, at constant temperature and pressure, which we've expressed as the summation of the chemical potentials times the D and I, okay, this will evolve so that dG will decrease, okay? So again, we can suppose that the system reacts, okay, according to a particular reversible reaction. So this is our little machine that will allow us to conserve atoms and change along this line, change the number of the composition essentially. So D prime Mi, forward and backwards. Ni double prime I Mi. Okay, so this is my little composition changing, atom preserving little mechanism. Okay. We know that by definition of the progress variable, okay, in differential form dNi, okay, which appears here, can be expressed as ni double prime I minus ni prime, okay, times the differential of the progress variable, okay. So how do we write this condition here? The directions towards which spontaneously we evolve. Well, you can hear me, right?
Yes, Professor.
Very good. So I'm just rewriting it, okay? Now let's substitute for dNi, let's substitute this expression here, okay? Okay, and this multiplies essentially the same, I'll put it outside, d psi, and this must be negative, okay? So dG decreases, okay? So for any d psi, so for any direction that we're taking along the reaction, whether we're going from left to right, from left or from right to left, really the system spontaneously will respond, well, not, forget that. Whether spontaneously the reaction is proceeding from left to right or from right to left, okay, dG must always be decreasing, okay? So essentially, dG at constant temperature and pressure being less than 0 holds always, okay? Whether d psi can be bigger or smaller than 0, okay? So suppose, for example, that we're proceeding from left to right, okay? So the progress variable is increasing, so d psi is positive, so we're going from left to right in the reaction, okay? From hydrogen and oxygen to water, towards the formation of water. So clearly, the progress variable, as I said, increases. The top arrow says that it's increasing, okay? So look at this. If this is positive, then clearly if I divide, okay, by d psi, this must be less than 0. Okay? Less or equal to 0. Okay? Again, going from left to right. On the other hand, the opposite really applies if we're going from right to left, like this. Right? Now, psi is decreasing, okay, it's negative, d psi is negative, and so essentially dg by d psi must be bigger or equal to 0, okay, because this is negative. Because dg is always, by definition of spontaneous direction, is always negative. Think of it, again, dg holds essentially the truth about the system, holds in itself the statistical interpretation of the system, okay, in terms of probability of a single configuration. Remember? So the system will always drive itself towards those configurations that are more probable, where the packets of energy are more spread out. Okay? And in this particular case, when you're talking about a particular composition of a system, you're really saying what is the most likely composition, okay, that allows for more configurations, okay, energetic configurations. And so look at what the conclusion that we said. On the other hand, psi tells us, so this is G, okay, what the meaning of G, but psi just tells us in what direction the composition is changing, right? So look what we wrote here. We've related, in some sense, the slope of a function, okay, G of the progress variable psi, okay? And this gives me the idea that maybe I can actually draw it. Okay, I have as an independent variable my progress variable. For example, in the simplest case, varying from 0 to 1. Okay, and this is my Gibbs energy as a function of the progress variable. Okay. So I said, if we're proceeding from left to right, if I start from 0 and going going right from left, okay, the slope is decreasing. So it's something like this, right? On the other hand, if I start from the right and go to the left, you see what's happening. The slope is positive. So obviously, the general shape is something like this. There will be a point here where, oops, okay, where my dg by the psi is equal to 0, a minimum of Gibbs energy, okay, and this will be the equilibrium, okay, value of my progress variable. So my system will evolve, but spontaneously it will drive itself towards this point here, okay? Which is in between. It's not completely shifted to the left, it's not completely shifted to the right, it's somewhere in between. And because now if I were able to write down this function explicitly, I would be able to find this particular value of xi. And so I know the equilibrium composition is equal to the initial composition plus ni, which is the reaction, and we'll move along this vector only partially, okay? by substituting this value, which is not 0, is not 1, it's in between, okay? Psi of equilibrium. And in fact, we can do all sorts of stuff, because now we can also explicitly write dg by dx psi explicitly, because here it is, okay? If you divide by xi. So really my condition of equilibrium, okay, and this is really important, can be rewritten as this function here, dg by dx psi equal to 0, okay? I'll put it in a box because this is quite important, okay? This is the condition of equilibrium, okay? We have translated a minimum of Gibbs energy to the sum of the chemical potential multiplied by the difference in stoichiometric coefficients. I sum on all species, and this will be equal to 0, okay? If I have one particular reaction in my system. So you see how we're getting closer and closer to really being able to actually find our composition of equilibrium, okay? Which is, again, this. Geometrically speaking, if I can go up a little bit, what does this mean? Well, we know that we're moving along this line, okay? Believe it or not, this is a line. This is the initial composition. This will be completely shifted to the left. Where is my equilibrium point? Well, maybe here. Okay, this is psi 0, this is psi 1, okay? And in between, we will have point of equilibrium. How do we find this point of equilibrium? Well, again, if I am to draw the picture I just drew, with this being G, okay, I'm just putting the graph along this vector, okay? This is G, okay? This is a minimum of Gibbs energy over here, okay? I hope that's generally clear what I just said, okay? Now, any questions about this? We're moving towards, let me just add here the fact that the slope here is negative and the slope here is positive, okay? Now, look at this expression here. It kind of is pretty intuitive that at some point, because we have to write down this equation, okay? At some point, I'm going to have to find an expression for the chemical potential. And this is what we're going to be doing later on, where for a mixture, okay, of ideal gases, we're going to write down an expression for an explicit, okay, expression for the chemical potential. Okay, but we haven't finished about chemical reactions. We haven't finished because we have to generalize the theory here. I mean, I've only given you here a hint of what's going on here. I've given you an initial composition, and I figured out how to write down two planes, okay? And it turns out that for a system of 3 species, okay, and 2 atomic species, okay, there is only one sort of stoichiometric vector, okay? So we're essentially moving along a line. That essentially means that if I take 3 species, okay, there's only one way I can write a stoichiometric relation between the 3 species, okay, O2, H2, and H2O, that will ultimately conserve my hydrogen and oxygen atoms, okay? There is not another one. Or if there is, it's a linear it's the same multiplied by a factor, okay? Now, let's try and generalize this. What about if I have any species composed of any number of atoms, okay? How many, we call them independent stoichiometric relations or reactions, do I have among any combination of species so that atoms are overall conserved, okay? But not necessarily I will be moving along just a straight line, okay? There may be multiple lines, multiple stoichiometric vectors doing that. And so I will probably be moving along a plane, okay, generated by these 2 stoichiometric vectors, okay? So I really need to generalize this concept, okay? And I'll try to do it in the easiest way possible so that it's not too vague, okay? So I'll just start, okay? Well, we have 5 minutes extra, so I have another 10 minutes. So let's see what we've figured out so far. A reaction, okay, is represented by a stoichiometric vector Ni, okay, this is what we said, in the space, okay, what dimension does this space have? Well, if we generalize, it will have the dimension equal to the number of species. So NS, we call NS the number of species. Before it was just 3, it could be anything now, okay? It could be 10, it could be 50, okay? So a particular vector, okay, will be, in this space, will represent a reaction, okay? So that's what we have seen. Now, we want to address the question, given a chemical system, for example, a chemical system could be a system composed of, say, species H2, O2, H2O, which was the system we saw before. We can add any other species. For example, let's add the radical OH. Okay, now we're living in R4. Okay, so it's a little bit more complicated. Okay, so if I give you this bigger, okay, chemical systems, how many independent reactions are there? In how many different ways can I react these 4 substances in order for the total number of atoms to stay constant, okay? So let me generalize this. So we've seen that we have NS, which is the number of species. And let me write down the number of elements or atoms, okay, as being Ne. So this is the number of atoms, okay? So in this particular case, we have 4 species, so I'm numbering them. Remember that the numbering of the species is very important because I need to keep track of them. So this will be species 1, species 2, species 3, species 4, okay? So NS is equal to 4. And the number of atoms, well, what atoms do I have? I have just simply hydrogen and oxygen. Atoms are also called elements or elemental species, okay? And again, I can order them so that the hydrogen number atoms is number 1, and I add the oxygen atom is number 2, okay? Now, one thing that we have seen is that particular matrix. Remember the matrix that we saw before, the 2 by 3 matrix? So that matrix is something that can be generalized. Let's call it matrix A. Matrix A will contain elements ij, okay? And it will be a matrix which will have essentially 2 rows in this particular case. So NE rows and as many columns as the number of species. So this is how we write it. It belongs to NE times NS, okay? Space. And what does it contain? Well, it contains these elements ij, okay? So I is the row and j is the column, okay? And it contains the number, I mean, this little hash thing is the number of atoms, okay, of element I in the species J. Okay, so it's far easier if I write it down. Okay. Let me see if I need to let somebody in. Okay. Yes, we're finishing at 11:50 today. I think, yes. So my matrix A now is what? Well, again, as I said, it's a 2 by 4 matrix where essentially you have 2 rows, okay, and 4 columns, okay? So each row, each of the 2 rows, okay, represents essentially the elemental species. So hydrogen is in row number 1 and oxygen is in row number 2, okay? And the columns, on the other hand, represent the species. So species 1, okay, is hydrogen and so on. Species 2 is oxygen. 3 is water. And 4 is OH, right? So now you can fill this in because you have to fill in the number of atoms of each element in the particular species. So for example, how many atoms of H do I have in hydrogen? 2. How many atoms of O do I have in hydrogen? 0. How many hydrogen of H do I have in oxygen? 0. How many atoms of O do I have in oxygen? 2, and so on, okay? 2, 1, and 1, 1. Okay, very easy to fill in, okay? Now, in these last 3 minutes, I'll show you how we can essentially determine the concept, write down formally the conservation of atom. Okay. So you've seen that. Maybe I'll remind you. That multiplying the matrix, this particular matrix, so you see that we had introduced it already before. by the composition, the instantaneous number of moles that we have, we end up having, I'll write it here, the elemental composition, NH and NO, right? We can generalize this by saying that wherever I am in my phase space R and S, okay, suppose I have an infinitesimal change in composition in my phase space R and S, okay? If I multiply A, or apply, should I say, matrix A to Dn, what I do get, okay, is, as we saw, the variation in the number of moles of the elements, okay? What this means is again, I'll say it again. What A does applied to any vector representing a composition is will give you the number of moles of the elements. So again, if I apply it to an infinitesimal variation, okay, of the number of moles, I will get the infinitesimal variation of the number of moles of the atoms. But what's the infinitesimal variation in the number of moles of atoms? What should it be? It must be 0. You agree? Because the number of moles of atoms doesn't change. It's always constant. So this position here formally represents conservation of atoms. It is a constraint, okay, on the direction I can take, okay, in our, well, in this case it's R4, so let's take a projection. I cannot take Dn anywhere, okay? I cannot go anywhere, okay? I have to choose Dn so that ADN is equal to 0, okay? And next time I'll show you that a vector, Dn, or any vector, okay, having this particular property that when applied to matrix A, it gives the 0 vector, means that the vector Dn must be not anywhere in Rn, okay, but it must be in a special subspace of Rn called the kernel of A, okay? The kernel or null space. Okay, you probably have, oops, null space. You probably have seen this already in linear algebra. It's a special subset, or it's a vector space, which is a special subset of Rn, okay? So, long story short, okay, I'm living in Rn here, but I cannot move around anywhere. I really need to be in a subspace of Rn, which we call the kernel of this particular matrix A. And I'll tell you how to find a basis for this subspace. And once we found the basis for that, we have found independent vectors that actually generate this subspace. And therefore, we found the independent reactions, okay, that we're interested in. But this, we'll do it next time. I'm stuck now, okay. Oh, it's not working anymore. Okay.